Hey everybody, back to our t-tests. We decided already that we're going to be using t-tests whenever we're trying to compare two different means. We have two samples we've collected and we want to see if their means are different from each other. And we have to meet the assumptions of normality and equal variance, at least if we're using the traditional formulas. We will have other options for non-parametric tests when we're in JUMP. But we also have to know whether or not our samples are independent of each other or dependent. And so we've covered the independent tests. Now let's move on to the dependent t-test. Just as a quick review, we know we're going to be running a dependent t-test when we have a continuous response variable. We're looking for differences. We have two different samples or groups that we want to compare, and these samples are not independent of each other. In other words, they are dependent on each other. Sometimes you'll hear this referred to as a matched pairs t-test, because the point of having a dependent t-test is that you know your observations actually come in pairs. You can link the observation from one sample to a very specific observation in the other sample, hence they are matched. What's really interesting about these paired studies, anything that has a dependent t-test involved, is that they're really powerful because they're controlling for a lot of the other variability you might otherwise see between the two observations, the sets of observations. So as an example, there are lots of paired watershed studies across the country where they might apply a treatment. Here is an example where they did a clear cut and an herbicide application to one watershed at Hubbard Brook, and they left the other adjacent watershed with the same slope, the same elevation range, the same aspect, the same species composition, the same soil type. So they left that one uncut and had weirs at the bottom of both to be able to compare how the two watersheds differ. So you're controlling for all these other possible sources of variability. Another example on a smaller scale would be paired plots, where you would have one plot that's been treated with whatever it is you're testing for, and another control plot that has not been treated. Again, because these are dependent on each other geographically, they're matched pairs purposely linked together so that we can control for all these other potential sources of variability. These matched pair studies are also really common in other fields because of this power, this ability to really be able to isolate a treatment effect by controlling for all those other sources of differences that you don't care about. But the key to harnessing this power is knowing which observations should be matched to which other ones. And because of that, we want to set up our data table in both Excel and in JUMP a little bit differently so that the information about which observations are matched is very clear. And also, because we're really talking about differences between these matched pairs and not really differences between the means of the two groups, what we're going to be doing is a little bit different mathematically. We're actually going to look at the differences between each pair. So it's these paired differences. This is pretty similar to the independent t-test, but instead of running that test on the difference of the means in the numerator, we're really going to be looking at the sum of these paired differences. The dependent t-test has the same assumptions as the independent t-test. We have to have normally distributed data, but be very careful here. It's not that the actual observations have to be normally distributed. It's that the difference between all of the pairs has to be normally distributed. So in order to test for normality on this test, you have to actually create a new column where you're calculating the difference between every one of the matched pairs. And then you would run your goodness of fit test on this difference column. So to calculate that obtained value, that test statistic for the dependent t-test, here we are changing that numerator. Again, we're going to be looking at the difference between every single pair of observations. We're going to calculate that and then we're going to sum them all up. That's what this sigma is telling us. Sum up all of those paired differences. And then again, in the denominator, we have something that looks a little bit similar to what we had before with the independent t-test. But now instead of using all of these different sample sizes, again, we're just substituting in the differences. Not super complex algebra, but you do have to be very careful because, for example, notice that what this is telling you is to take the difference that you've calculated, square it for every single observation, and then sum all of those up. Whereas what this one is telling you is to take the sum of all of those differences, same as the numerator, and then square that one number. Remember that we have these sample sizes, these n's in here, as a way to bring power into the test statistic that we're calculating. Notice that how we're going to calculate the degrees of freedom for this dependent t-test is different from how we did it with the independent t-test. All we have to do is take our sample size, which is the number of paired samples, of paired observations. It is not the total number of measurements made, it's the number of pairs. So again, I feel like I should have a little alert sign here, like alert, 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 alert. Okay, your n is the number of paired samples. Figure that out, subtract 1, and you've got your degrees of freedom, which you know you're going to need to use your table to find your critical value. Even though the formula to calculate that obtained value is different for the dependent t-test, the table that we use to identify the critical value to compare that to is the exact same table that we used with the independent t-test, and we're going to use it the exact same way. We know that we have to figure out whether we're doing a one or two-tailed test, and that will usually bring us to the right table, right? And then we just need to find the column with the significance level, that alpha threshold that we've picked, usually 0.05, and then we find our degrees of freedom in the rows, and that will bring us to the right location. So if our degrees of freedom are now n-1, notice this is going to bring you to a different row than that independent t-test would have. If what you calculated with the formula was more extreme than what you find in the table, then you know you have a significant difference between those paired samples. If it's less extreme than what's in this, then you know you do not have a significant difference. In Excel, we already talked about the function for the t-test. The only difference when we're trying to get a dependent t-test instead of an independent t-test is that we have to select a different input number for that last input option in the function. So we would enter equals t.test, and then inside of those parentheses, we would highlight the first array for that first sample. We would then, highlight the second array, and again, they have to be ordered so that Excel knows that the same order matches those samples together, that the first observation in this array should be matched with the first observation in this array. We enter a comma, tell it how many tails we're doing for our test, enter a comma, and then this time we would enter the 1 to get that paired or dependent t-test. Keep in mind that the one downside to doing this in Excel is that the output of that function is only giving you the p-value, the probability for that test. It's not also giving you the obtained test statistic, which you would need to report in your summary. So if you're doing it in Excel using this function, you'd still have to go back through and use the formula to calculate that obtained test statistic. Doing this all in JMP is much easier, but you have to make sure you've got your data table set up correctly, or else you won't even be able to run the test. So to get a dependent d-test, a match pairs t-test in JMP, you have to have these two different samples set up again so that each paired observation is on the same row. And the way that you can think of it is that really each of my degrees of freedom, right, each of my n's, when I'm calculating my degrees of freedom, should have its own row. So this pair belongs together, this pair belongs together. If you don't have it set up like this, you won't even be able to get to the dependent t-test platform. Right? So how do we do that? Again, we're in that Analyze tab in the main toolbar. We come down right here to its very own platform, Matched Pairs. And when we click on this, it's going to ask us to enter two different columns because, again, these two samples are side by side and we have to enter both of them into this paired response. So we're entering both of these continuous variables into the paired response box. When you click OK, you're going to get a new output window that can seem a little overwhelming. There's a lot of information packed into this one little set of output here. The graph is a little bit different than what we're used to seeing. On the x-axis, we have the mean of both responses. So you take the pair, what was the mean value for that pair, and then over on the y-axis, it's the difference. And JMP is telling you which way it calculated that difference, so you know which sample was subtracted from which other sample. The gray horizontal line here in the diamond is showing you the 0 or no difference level, so what you would expect to see if there were no difference between these two paired samples. The red horizontal line here is showing you the mean difference, so on average, how were the two samples different from each other. The dotted red lines on either side of that are giving you a 95% confidence interval for that mean difference. So you know you can say with 95% probability that if you were to collect more samples or represent the entire population, that this mean difference would fall somewhere in between these two confidence intervals. And a really quick and dirty visual is that if these 95% confidence intervals do not overlap this 0 gray bar, then you probably have a significant difference, because even with 95% probability, you know that you're not going to fall or cross into that 0 value range. This visual also helps you to examine individual observations, maybe do some quality control, look for outliers or really interesting observations. And so, for example, what we're seeing with this data is that the higher the mean value for those paired observations, the more likely you are to have a negative difference, whereas the lower the mean value, the more likely you are to have a positive difference. So let me back up and just point out, maybe I hadn't said this yet, anything that falls below this 0 line is a negative difference when you're subtracting in this order, and anything above that 0 line is a positive difference when you're subtracting in that order. So this one little visual gives us a lot of information without even having to come down into the actual statistical output. We do need to come down here, and we have a lot of information. First of all, JMP is giving us the means for both of our sample groups. Right? So that would be the mean of group 1 and the mean of group 2. It's also telling us the mean difference between those two groups. So on average, how much were those paired observations different from each other? It's giving us the standard error for that mean difference, and again, the confidence intervals about that mean. So it's really just telling us what the values are for all of these lines. It's telling us how many paired observations we have. It gives us a correlation between those two, and we'll get into this a little bit more when we move into looking for relationships. But essentially, this correlation is trying to tell you how much of the variance between these observations can be accounted for by this one treatment. So if you see that you have a higher alcohol, do you also have a higher no alcohol? So in other words, it's looking to see if you see a similar trend. This T ratio, this is our calculated or obtained test statistic. So this is what we would report in our summary. This was how many degrees of freedom there were for this test, and here it makes sense because it's not using a special formula for unequal variance. So we can see we had 20 observations. That n minus 1 gives us 19 for our degrees of freedom. And then we have the 3 different types of probabilities that we might want. The two-tailed probability, the right-tailed probability, and the left-tailed probability. Because when you're in JMP, you're not controlling which group is subtracted from which other group, it can be hard to figure out whether you're hypothesizing a right-tailed test or a left-tailed test, or really even how to interpret this visualization. So JMP tries to make it a little bit easier. As we mentioned, it already tells you exactly the direction that it was doing that subtraction in. Right? So as an example here, we had an alcohol observation, and then the non-alcohol replicate of that was subtracted. So the key is to try to figure out which tailed test you'd be using, is to figure out whether or not your hypothesis would have expected this to be a positive test statistic or a negative test statistic. Right? So if you had hypothesized that your alcohol was higher than your no alcohol, so a higher number minus a smaller number is still a positive number. So that means you would expect a positive test statistic, and therefore you'd be doing a right-tailed test. Here's your right-tailed test pointing towards the positive direction. If, on the other hand, you had hypothesized that no alcohol was higher, then that means you would have had a smaller number subtracting a bigger number. It gives you a negative test statistic. Then you would have been interpreting that left-tailed test. Okay? Another way to think about it is, because of the order, you can literally just stick the two group names in the same order on either side of the caret, and it'll tell you the same thing. So if I hypothesized that alcohol, keeping that order, if I hypothesized that alcohol was greater than, there's my greater than caret, no alcohol, I would use this one. If I had hypothesized that my alcohol was less than my no alcohol, then I would use this one. Okay, and JMP also tries to put these within the figure as well, so that you can see which observations had a higher alcohol response versus those observations that had a higher no alcohol response. Right? And just like with the independent t-test, we have an option for a non-parametric test if we find that that difference column is not normally distributed. And it's another Wilcoxon test. So again, virtually the same formula as we were using for our dependent t-test, the parametric version, except we're ranking all of the data and we're using those ranks for our calculations instead of the raw measured values. And we can get to that, again, from our magic red triangle. So if you're in your JUMP output, you can come right into the magic red triangle and select the Wilcoxon signed rank test, and it's going to give you all three of your probabilities, your two-tailed, your right-tailed, and your left-tailed, all tacked on to the end of all of your output. So at this point, you should have a general understanding of how you would run a dependent t-test by hand using the good old-fashioned formula and tables, in Excel if you wanted to use the Excel functions, or in JUMP. And hopefully you now also know when you would run a dependent t-test. But regardless of what test you're running, you still have to get through actually summarizing all of those results. And basically, we're trying to write a one-paragraph abstract-like summary of what we've done. And this summary should include a statement of what your original test was. This is going to tell us whether or not you were doing a one-tailed or a two-tailed test. If you want, you can give a little one-sentence summary of the general methods that were used to collect the data. You're going to report your results, and the way that we report that shorthand is the same as we would use for the t-test. So we'll go back and look at that. Remember, we specify that with the t, that we're doing the t-test, we enter our degrees of freedom in the brackets. We report the calculated or obtained test statistic that we used, and then report the p-value associated with that test. So all of that would be in brackets, shorthanded within your sentence that basically summarizes whether or not there was or was not a significant difference between your two groups. Okay? And then you're going to want to interpret that. So you want to describe what the difference was like. Was the first sample larger than the second one? Did the response increase or decrease with the second group? And what this means. Give me some big picture. Overall, what does this indicate? And what does this tell you about your original research question? And to do this well, it would be great if you can get all this information into a really concise paragraph that flowed and seemed well written and was essentially communicating what could be seen as complex information in a very clear way. When you're doing these t-tests, if you do find a significant result, it's also really helpful to do that Cohen's effect size to see if you also have a likely meaningful result. Again, this is taking the power out of the equation quite literally. So you can use this exact same formula for the dependent t-test because, again, you're just trying to summarize how different on average those two groups are. So you would take the mean of the first sample, subtract the mean of the second sample, and then just divide it by their average standard deviation. And again, this is going to give you an idea of whether or not there's likely a very small effect, and maybe you only found a significant result because you had a very high power to your test. If you're somewhere between 0.2 and 0.5 for that Cohen's effect size, you probably have a medium effect. And once you get up over 0.5, now you're talking about not only a significant result, but also something with a rather large and meaningful effect. So that about sums it up for our dependent t-tests. Hopefully you understand when to use these, and you have several different options for how you might